Welcome everyone to day 3 of the MPC Retreat. So it is my pleasure to welcome Girisha Shankar. Girisha Shankar is a postdoctoral researcher in the Department of Computer Science and Automation at IISc Bangalore, working under the guidance of Dr. Bhavna Kanakurti. His research focuses on cryptography with particular interest in rational cryptography, post-quantum secure constructions, and foundational cryptographic problems. Girisha holds a PhD from IISc, an M.Tech in Communication Systems from IIT Kanpur, and a BE in Electronics from RVCE Bangalore. Before transitioning to academia, he had a distinguished industry career spanning over 2 decades, most recently leading the data center security team at Cisco Systems. His work has been published at top-tier venues including ACM CCS and the Cloud Computing Security Workshop. So today he'll talk to us about solution concepts for rational secure computation.
Thank you for the kind introduction. Let me start by thanking the organizers for this opportunity to share my work. So, today we will be talking about some of the solution concepts that are relevant in the context of rational cryptography, especially when applied to the MPC setting. So, this is a joint work with my PhD advisors and other collaborators. So, here's a quick outline. Many of you are familiar with the setting of MPC already. So, here again, just to recall, we have a set of parties with their private inputs, and they are interested to compute some function f on their private inputs. Of course, this can be done in different ways, especially if all of them can send it to their trusted party, they can easily do it. But being cryptographers, we would want to avoid that kind of a thing, and instead we want to rely on some kind of a protocol, an interactive protocol at that, which can do the same. And we have the seminal results from Yao, the government circuits one, and also Goldish, Micali, and Peterson, who showed that any function can be computed securely under certain conditions, of course. In such a setting, we consider an adversarial model where we have a centralized adversary who can corrupt certain a subset of the parties within the who are participating in the protocol. And depending on the kind of this corruption, we can have either a semi-honest model where parties are expected to follow the protocol honestly, but can be curious to glean information from the protocol transcript. Or we can also consider a malicious setting where we let the parties to deviate arbitrarily. I just want to make one observation here, which will be useful down the line, that in both these models, we assume that parties who are not corrupted to stay honest. Okay. Now, many times this may not really be the case. The reason being that often we come across parties who may be participating because of their own self-interest. Okay. So again, being cryptographers, if you want to design some protocol, an MPC protocol at that, our goal is to achieve the best, be it in terms of the security level, be it in terms of the efficiency, at the same time making as weak assumption as possible, I mean realistic assumptions, not relying on some idealistic models like say for example random oracles and so on. But as it often happens when we do these things, it's a trade-off. We often have to make away with at most 2 of them while compromising on the one of them. So the reality is that we can most often end up having 2 of these realized while compromising on the third. I want to specifically focus on the security level itself. I mentioned that we have either the semi-honest model or the malicious security model, right? Semi-honest setting is somewhere wherein we assume the parties to stay honest. Sort of a weak model at that, right? And on the other hand, which is, I mean, usually not realistic, we cannot expect parties not to cheat at all. On the other hand, when we consider a malicious security model, it's at the other end of the spectrum where we let the parties to deviate arbitrarily, meaning do anything they want. Because of that, that often leads to design of protocols which may not necessarily be efficient. Now we want to ask the question: is there something midway, and can we drop the assumption of everybody being honest? So let's digress now. Take just a brief detour to visit the when we model these protocols as games, and the parties we consider here are self-interested agents, meaning they are participating in the protocol because of what's in it for them. These are the parties with endowed with certain utilities which they like to maximize, and they also have a set of actions defined for them which they can use. And because they have certain preferences, that motivates their actions during the protocol. That's what we want to use. This is where we can make use of some of the tools and techniques from the game theoretic setting, and the typical one being the equilibrium. What's an equilibrium after all? An equilibrium is nothing but a set of actions or a strategic profile, as we call it, wherein at the equilibrium, if it holds, our parties get the best utility and without any reason or an incentive to unilaterally deviate from such a profile. Okay? So there are usually two kinds of equilibria we consider. I mean, there are other variants, but for our purpose, we can do with these two for now. Nash equilibrium, many of you would have already heard about it. Here, the best response for each of the parties, that is, best behavior for each of the parties, holds as long as in the equilibrium, if and only if all the other parties participating in the protocol also follow the best response. Okay? So in some sense it is dependent on others' response also. And there can be multitude of Nash equilibria in a given game. Most importantly, if we are considering a finite game, meaning a protocol with finite number of actions there, then by famous theorem from Nash, it's always guaranteed that there exists a Nash equilibrium. However, there can be more than one of them though. On the other hand, we can also have another variant of an equilibrium which we call as dominant strategic equilibrium. In this case, unlike the previous setting, the best response for each party holds in the equilibrium no matter what other parties do. Okay. Notice the contrast in this compared to the Nash equilibrium, where we say that the best response holds only if all the others also follow the best response. Okay. But since this is a stronger notion of equilibrium, it may or may not exist in every possible game. And when it exists, it would be a unique one. Okay? So far with me? Okay. But at this point, you might be wondering, I didn't say anything about what the parties are. But when we come to cryptography, we typically consider parties who are computationally bounded. Recall that every other theorem in our cryptography says for all PPT adversaries, there exists a negligible function and so on, right? How do we handle that? That is where we consider the notion of computational equilibrium. This is something that has been in research for nearly a quarter century now. The first notion of computational Nash equilibrium was introduced by Doris, Halevi and Rabin back in 2000. They considered a setting of two parties, and the Nash equilibrium is pretty much the same like what we saw. Either party has no incentive to deviate unilaterally, provided other party is also holding on to the good behavior, let's say. This was extended to a multi-party setting by cards later. One other thing I want to also highlight is that in the case of a normal game, we didn't make any assumption with respect to the parties' computational capabilities. But here, they always, we let the parties to win or to break the protocol with a negligible probability, right? Because of that, it's always possible that the if we model a protocol as a game, a cryptographic protocol as a game, there always exists possibility that the adversary may win, although with negligible probability. So we consider that parties do not care about these negligible gains, because even if they win, say for example, if I were to guess the secret key, I can let's say make a fortune, but that can happen with a very small probability, and in expectation that overall gain would be so small I can possibly ignore it. So we consider that parties are indifferent to such negligible gains. Moving on, the whatever I told you about computer. Yeah. Yeah, unilateral deviation means a single party deviating. But they have a very good question. What there is no guarantee if two parties deviate. For example, a bilateral deviation happens. There is no guarantee on the equilibrium. Okay. So the notions that we just now talked about considered only the utilities which had monetary considerations, but didn't handle the privacy explicitly. It was work of Milterstein et al. Back in 2009 who for the first time considered privacy as part of this equilibrium setting, and they considered two notions, that is monetary and information utilities, to be part of such an equilibrium. They assume that as long as there can be leakage, but as long as that leakage is bounded within certain limit, the equilibrium can hold, with a further assumption that the parties would value their monetary gains more than the privacy gains. Okay, with that assumption, they showed that there exists privacy what they call as privacy enhanced computational Nash equilibrium. And there is also another work by Katz, Garay, and Maurer, and so on, who designed this notion of rational protocol design. Here, it was it was designed as a two-party game where we have a protocol designer on one side and the adversary on the other side. Goal of the adversary is to attempt to break the protocol by inducing corruptions on the parties. So each such corruption would have some cost, and also because the adversary is trying to do this, there can be some gains for the adversary in return. The protocol would meaning the equilibrium would hold as long as the gains made by the breach are less than the cost of making those breaches. Okay, so they also showed that a Nash equilibrium holds in this. Both these works, and in fact almost every other work that we see in at rational cryptographic setting made use of this Nash equilibrium. So to summarize, on the one hand we have the MPC setting, the classical MPC setting, where we consider the adversarial models we saw, and moreover we assume that parties stay honest when not corrupted, without considering their individual preferences. Then we typically show the security by presenting a simulator, as you all know. Then when you come to the rational cryptographic models, we consider parties are no longer assumed to be honest. They are rational. They can behave motivated by their preferences. And lastly, we consider equilibrium notions for security. We may be wondering as to is there a way we can realize both these? Is there a way to have best of both these worlds? Indeed, we show that it's possible. We can show that following the protocol honestly is indeed the best response, and we can also guarantee a full privacy by making use of cryptographic techniques. So that's what we introduce as privacy preserving computational dominant strategy equilibrium as one of the solutions. Yes.
So, what do you assume about the preferences of each party, like when you model this thing?
It depends very much on the game actually. We'll down the line we'll see.
But, like, you have to assume something, right?
Yes. For example, let's say we show auctions wherein depending on it depends on very much on the game.
Okay, so for specific protocol, the preferences will be different.
Will be different, yes. So here's a quick illustration of what this equilibrium notion means. We can have parties either being honest or play cheat, right? And our goal is to make sure that whenever they are playing cheat, we would want to dissuade them from doing so, since they are rational, by suitable penalties. So as a result, since they care about their utilities, they don't want that to be reduced, so they would stick to honest behavior. Right? Are we done? Not really. Why? Because we know that we already have a semi-honest model wherein even if parties play honestly, they can still attempt to glean information from the protocol transcript, right? Which we want to protect. So as a result, what we end up getting is a privacy preserving computational dominant strategy equilibrium. Notice that in this case, we are explicitly calling out the dominant strategy equilibrium instead of Nash equilibrium. So informally, so what it means is following the protocol honestly would be the best response for every party, irrespective of what other parties would do in the protocol. Secondly, there exists a simulator. What it essentially means is no party learns anything more than what the protocol outputs or whatever you can derive out of it. Okay? So that's about this first solution concept.
So over here again, privacy is ensured only like for a collision threshold of 1, right? Like if two parties collude, then still privacy is ensured.
Hold on that. That's the coming up. That's the next one. We will be trying to collision. Right? Yeah.
The party is to follow the protocol correctly.
Yeah.
Is this like when they say in the like does this have an application in like blockchain where the parties are?
In fact, one of our works has been ported onto blockchain also. I mean, depends on the protocol. Depends on the application that you want to run. Yes, possibly yes, you can do that. Any other question? Okay. As Bhavish was saying, the next other thing that we want to consider is the collusion resistance. In a typical MPC, what happens? We consider that the model is such that as long as collusion is, by the way, allowed, right? But within certain threshold. As long as parties collude within the threshold, no harm done. That's the guarantee that we get, right? That's from the traditional MPC. As well in the rational collusion models also, there are these notions of T resiliency, wherein parties, what you call T lateral deviations are can be sustained. Just to answer that question that you had, okay? But we want to look at collusion in a very different way. Okay, just to say, as long as parties are within certain threshold, no harm done there. We want to look at it a very different way. We want to ask the question, is there a way, since we are considering rational parties, is there a way we can incentivize the parties from even forming the collusion in the first place? Okay. For this, what we do is we assume that parties can be privacy sensitive, meaning they would not want to divulge their own privacy, even if it means to learn something about other parties' private inputs. Okay, they value their own privacy first, more than what they can learn from the others. Under this condition, we show that it is possible to have a setting where parties can be dissuaded from forming the collusion in the first place. Okay, so if it is not viable for them, the collusion itself will not be there. So these are the two solution concepts that we introduced. Now I want to quickly run through the application of these solution concepts in a canonical application, that is auctions, which is all of us know what auctions are. It gets used by whether it is in some artwork or some sports franchisee and so on. But closer home, it was the first application of MPC itself. Back in 2008, the MPC was used for running auctions for Danish sugar beets auction. So in our work, I'll be considering for today's presentation the first prize auctions. So what is the first prize auction? Here we have a set of parties with their private inputs. Our goal is to identify the winner, who happens to be the highest bidder, and also to compute the highest bid itself. There's no fun if there's no constraints, right? The constraint is that the losing bids are not leaked at all, meaning nobody learns about the losing bid values. So at the end of it, the output should be only be the identity of the winner and the highest bid values. There are various ways to do this, by the way. Auctions have been looked into from MPC point of view in various settings. One very natural way of doing it would be integer comparison protocols. However, as you can realize, integer comparison is a costly operation, and moreover, when you do that, it actually leaks the rank ordering of the bits, even though the actual bits themselves may not be leaked. Secondly, we also have commit and reveal paradigm used. Commit to the bids, then to the auctioneer, and after some time in the reveal phase, reveal the bids. Only the auctioneer will learn, and nobody would learn. There are some auctions. This is one auction which is used on blockchain itself. One can also make use of generic MPC. The Milton work that I mentioned earlier, in fact, does this. Lastly, we can also use bit slicing techniques. That is, compute the highest bit bitwise. So there is one particular protocol which is anonymous veto protocol, which we extended to call it as anonymous bidding protocol. So here is how the protocol itself runs. Suppose I have three parties with their bids shown in binary form there. And the protocol itself runs for as many rounds as the number of bits used in the binary representation. During each round, parties contribute their bits and write it onto the bulletin board. I mean, although I have shown all the bits in clear here, just for illustration, but in reality, they would be writing the encoded forms so that which they don't leak the values. So during each round, they contribute their encoded value, their bits from the bid, and at the end of, once all the bits are available, we just compute the logical OR of that. Fair enough? So at the end of first round, as you can see, the computed value is 1. In the second round, the party 1 contributes 0 while the other 2 contribute 1. Now the computed value is also 1. Now, as you can realize, the party 1 can no longer win the auction. Why? Because no matter what it contributes for the remaining rounds, its value will always be lesser than the computed round. So it will fall out of the race and is expected to only contribute zeros, even though it has ones as part of its bid. Okay. Likewise, the second bidder also contributes 0 in the third round and falls out of race for the remaining rounds. And ultimately, it is only the highest bidder who ends up contributing exactly the same bit values as it has, and so the computed value is exactly same as the highest bidder. So far with me? Assuming that all these bit values, all these bits were encoded without revealing the actual bits itself, seems to be fine. We are computing the values correctly, but there is still a problem. Consider this round where it's only the highest bidder who is contributing a 1, whereas others are contributing a 0. Which means the highest bidder, since the other two encoded bits are available on the bulletin board, possibly the highest bidder can make use of this to learn about the second highest bid value. In particular, it can learn that other two have contributed a 0, which means it has learned the first 3 bits of the second highest bidder, since they are exactly matching otherwise with the highest bidder. Evidently, it's a leakage, right? Which we want to avoid in our design. So, just to quickly run through the protocol design itself, as you saw, it's possible for the winner to learn the second highest bit, which we want to avoid by introducing an evaluator in place of everything available to the all parties on the bulletin board. But this doesn't really solve the problem, because what is evaluator itself is a winner. It can still learn, right? So we want to prevent the winner evaluator from learning if it happens to be the winner. So for this we make use of oblivious transfer. And then we also would want the parties to follow the protocol. Recall that our model considers parties to be rational. So we want to dissuade them from dishonesty. So we seek security deposits from them. And how do you even detect parties are deviating? Create proofs. And as you know, one natural way to do this would be use NISICs, right? But NISICs are expensive. They would bring down the efficiency. So instead we rely on some protocol specific proofs that suffice for us. Okay. Lastly, this I will explain later. Okay, so our protocol, we make use of this bitwise computation. Hence, we need some encoding scheme which can ensure that the encoding of 1 and 0 remain indistinguishable. We make use of a construction based on DDH assumption for this. So the parties send their encoded bits to the central evaluator for computing, who collects this only if it is not contributing a 1, and highest bit for that round is computed by the evaluator, written to the bulletin board. And as we saw, depending on what gets written to the bulletin board, the parties may fall out of race. Lastly, whoever wins can prove that they are indeed the winners and claim the option. Okay? So, how much time would I have?
Like 1 to 2 minutes if you could wrap up.
Oh, is it? Oh, some more time. 5 minutes would do.
I think we are running. We did start a couple of minutes late, so I've taken that into account. So if you could wrap up in 2 minutes, because you also would like questions.
Oh, fine. So let me just mention that what we do is in our protocol, since they are rational, we consider that parties do not cheat just for the heck of it, unlike a malicious setting, and hence they would they would not cheat to throw away their chances of winning the auction itself. So we do not go after detecting all possible cheating in our protocol. And secondly, we seek proofs of not winning from the parties if the winner doesn't come forward to win. So this happens only when parties cheat out of band, And as I mentioned, this without using physics, it helps us to detect the cheating. So, in the interest of time, let me skip other things. Just to mention that this protocol itself, I'll just directly jump to the security notion. So, what we show as part of the protocol itself is that there is no incentive for parties to behave in a deviating way, and any deviation would be irrational. We show that dominant strategy equilibrium exists for that, and when they are not deviating, we show that there is a simulator that exists which guarantees that nobody learns anything more than what the protocol allows. So, and we also show that collusion resistant, because evaluator alone would be part of, would get all the encoded bits and needs to be part of any meaningful collusion. And we show that whenever evaluator is part of the collusion, it reveals its own bit. And since we assume privacy sensitivity, evaluator cannot be part of any collusion, and hence there is no meaningful collusion. Okay, I'm sorry, I'm running through fast, but this is good. Okay, so we also compare our protocol with other existing ones and show that runtime and communication complexity is better. Yeah, that's it. Okay.
Questions?
So it seems to be like in rational setting, you're somehow forcing semionist behavior.
Not really. We are letting the parties to deviate.
Right, but in that you're showing, like you're making them, like you're ensuring that if they deviate, there is some penalty.
Yes, it is costly for them to deviate. Yes, exactly.
So does that mean if I have like a covert secure protocol, would that, you can directly compile it to a rational secure protocol?
Not really. What happens in a covert security protocol? Covert security means parties will deviate if there is no chance of getting caught. Correct? In our case, there are cases wherein parties will not even be detected. Cheating will not be detected.
Okay.
Okay. So that means they can deviate here.
Okay.
Just that we don't go after those deviations.
I see. Okay. And then you show that okay, even if they deviate that way, it's
Yeah.
not.
Yeah.
then
Thanks for
anything.
asking. This is a subtle distinction here. Yeah.
Okay. So that way, this would be more efficient.
Yes.
But
Exactly.
but that would still mean like if there's a covert secure protocol, I can get a rational protocol from that, right?
I mean, as I said, if you continue to model them as covert, you cannot get this, because you have to upgrade them to rational with utilities.
Right.
Then you can.
Yeah.
Yeah.
Like you just ensure that if they are caught cheating, they have to pay
Yes.
some penalty.
Yes.
or something.
Correct.
Okay, thank you. And also one more question. In this case also you are only considering unilateral deviation, right?
Yeah.
In your protocol.
They
Or
can
options.
no, in this case we can multilateral also.
Oh, okay.
But what we show is no matter what others do, the equilibrium holds.
I see. Oh,
Even if all the n-1 parties deviate, it makes sense for one party to stay on.
stay on. Oh, okay. Thank you.
Any other questions?
I have a question. So this seems very close to like cryptoeconomic security. This also seems related to cryptoeconomic security.
Economic security.
Yeah. So in this case, like for example, if a party deviates, how do you determine the penalty amount, which like makes sure that
Good
it's
question.
included?
So, in our setting, what we have done is the maximum value that they can gain from the any deviation plus some delta. That's what we have used. So that no matter what you can, there's no incentive for you to deviate. But that is highly protocol specific. I mean, it cannot be fixed by the model itself.
Thank you.
Other questions? So if not, we'll thank the speaker a bit.
Thank you.
So our second speaker is Madhav Natarajan. Madhav Natarajan is an MS student at IIIT Bangalore, specializing in cryptography under Professor Ashish Chowdhury. His academic work focuses on studying Byzantine agreement and broadcast problems under various network and adversary settings. Alongside his theoretical research, he explores practical systems engineering, applied cryptography, and distributed systems. Prior to his MS, he worked as an SDET at QNU Labs, developing testing programs and statistical validation suites for quantum key distribution, quantum random number generators, and hardware security modules. So Madhav will speak to us today on cryptographically secure domain extension for Byzantine agreement with improved round complexity.
Hello. Is this okay? So, hello, I'm Madhav. I'll be talking about domain extension protocol in the cryptographically secure setting with improved round complexity. There is a work that has been submitted to PODC 26. Hopefully it works. So we'll see what this is a fundamental distributed computing problem. So what is it? Basically, you have n parties. Each of them have an input, and the subset of t parties are maliciously corrupt. We say in this case we have an L-bit input for every party. So what does it do? Every party. The goal is that every party has to come to a conclusion of having a common output value, even when t of them are Byzantine corrupt. Okay? So there is a Byzantine. So all parties run a protocol and then come to a common output. So if we see what the security guarantees are, consistency. All honest parties have a common output V star, and if all honest parties do start with the same input, then all honest parties will have the same output V star, and so V star is equal to V. And liveness is that if all honest parties start with this, all honest parties do have an output. I mentioned that, so honest parties are the ones that are not under the power corruption of the adversary. That's part of the definition. Now, what is our setting here? So we consider a cryptographic security setting. So the adversary is a PPT adversary. And resilience is t less than n by 2, which is optimal. All their mentioned properties are achieved except with a negligible probability and error. And in addition to the parties being connected, they also have access to some cryptographic primitive or primitives in this case. The motivation is that the motivation for studying domain extension is that, let's say you have a multi-bit input, let's say L greater than 1. Your one bit BA protocol or BB protocol in this, for example, is costing O of n square or omega of n square. So you apply it for L bit in values. So you will have a resultant of omega of n square L bits of communication, which is clearly not optimal. The idea is that you apply a small number of Oracle access to BA protocol with small inputs, and then for a large input value you get linear computation complexity. So in doing so, we see to study these extension protocols, we come across 4 complexity measures to measure the performance of an extension protocol. So seed round complexity. So seed round complexity means the total number of communication bits. Seed communication complexity is the number of bits for which the BBBA oracle is invoked. Seed round is the total number of rounds in which the BB or BA oracle is being invoked. Total number of rounds and total communication complexity are self-explanatory, so we can go ahead. So our work compared to the prior work. So state of the art in this case is given by Naik et al. So they propose a 4-round cryptographic secure BA protocol with 2 seed rounds. We have managed to reduce it to 2 rounds in total with 1 seed round complexity. The same cryptographic primitives are being assumed as them. And both the measures that we have achieved, that is 2 rounds and 1 seed round, are probably optimal. Build yes.
Can you just explain what is seed round complexity?
Okay, so seed round is okay. So you have to achieve an L bit agreement on an L bit. You have to run agreement L times. For each, you call that 1 bit protocol. 1 bit protocol is what we have. Right? Instead, what we have is you have an L bit, but you achieve agreement by running or having Oracle access to small input. You agree on small inputs, and then you have smaller number of accesses to that Oracle program, Oracle BA. For example, imagine Oracle means some box that gives us agreement. So a black box type. You can't use that for for the entire L bits. For small inputs, get agreement, and so you can extend it for the entire input. So Oracle access.
The number of rounds where you are invoking the big graph.
Yeah. Okay. So the first building block that we see is a cryptographic accumulator. Cryptographic accumulator is basically a set of 4 algorithms. You have gen, eval, witness, create, and verify. So what it does is basically you have it maps a large set of values to a succinct accumulation value z. Okay? Now this z is O of kappa bits in value. Kappa is the security parameter. So I just want to say what this the data points. I just want to keep in mind. I'll explain what the data points are in the next and why I have grouped this as a set of tuples in the next slide. But that's one of the kind of gotcha moments of this protocol. But for now, just understand this as a large set of values mapped to a succinct accumulation value z, where using the second of the 4 algorithms, you can create a witness or a proof of existence for each element of this set using the accumulated key and the accumulation value. You can get a witness for each data point in the set. Now, I've used this. Here in our protocol, it is a tuple. Again, I'll use this word tuple throughout the protocol. What it does, and verify. So what does verify do? If given for this accumulation value, if you can have the data point and its witness, it is able to verify the membership of this element of this data point to the set against this accumulation value without having the entire set. So you don't need to communicate the entire set. So normally what you have to do, I'll send you the set, you will verify, you will perform the set verification and then say, whether this element belongs or not. Mathematically this does it, so we don't have to communicate the entire set. So we'll understand, first we'll collapse into a 3-round BA with 1 seed.
I missed something. So this is cryptographic construction?
Cryptographic, synchronous cryptographic.
So the primitive you just mentioned, which I didn't get fully, is it so what kind of cryptography is it? Fast function, or I see some collision resistance?
So collision resistance is that it is infeasible for an adversary
This
to.
is the property of this.
Property of the accumulator. It's there. It's proven.
Right. I'm just asking, what is the cryptographic assumption? thing relies on this accumulator?
It
Is it
is.
an independent thing or it relies on PRG, PRM, hash function?
Oh, okay. We saw the we saw how they've used it, and we kind
They
of
means
Nike et al. The previous the state of the art. They've used it as a black box and said this is what the guarantees are given for this. For this, refer to construction of bilinear accumulators by. Was that no? Aniket Kate was this one. There was one more construction of bilinear accumulators where they're able to get O of kappa bits of kappa bits of communication complexity in
that's
bit.
why you should know what is the cryptographic function it is relying on, right?
Okay. Can you
I mean, not
help me
now,
out?
later.
Yeah. And so this property will come into use later. Infeasibility for an adversary to generate a valid witness if the element does not belong to a set. Right? So we'll understand a 3-round PA protocol with 1 seed round first, and then later explain how we can collapse it into a 2-round with one seed round protocol. So first round, the high idea is very simple. So you see if a group of n minus t parties do indeed have the same input value, and if they don't have the same input value, we can safely terminate and then output default value. If they do, you basically have you encode the L bit input into you take into consideration via t degree polynomial into a RS code word. Again, that was one. We used the we encoded into n length code or RS code word polynomial, and here is where the tuple notion comes. So you form a set of tuples of the evaluation point and the evaluation value. For each party, what does it do? After it forms this set. Okay. So the accumulated key is assumed to be a priori available with all parties. Okay. So that is one point that is mentioned that I forgot to mention. Right. So you have every party does have this accumulation key and get the accumulation value of this set, and then once party PI gets the accumulation set accumulation value, it invokes an instance of broadcast and then send this accumulation value to all parties. Likewise, so every party does this, and you have every party in the end does have a vector of accumulation values. Now, every party does check if there are n minus t parties that have the same z. If it is, then go ahead. If it is not, terminate. So what does it do? Now, there is a set of parties which have the same z. Let us call that core. Now, what does it do? Now, what we have to do, with high probability, we can say that, collision, with high probability, the parties with the same z will have the same input. Right? And for honest parties in core, we can definitely say that it's true. So, what we do, now, the goal is the honest party in core has to make the honest party outside core agree on its input. So what does it do? Every party PI in core, it computes a witness for the jth component of its code word, creates a witness, and then send it to the party PJ who is outside core.
The identity of the core is known to everybody.
Yes, because we did broadcast. No, because we use broadcast. Everybody knows what is the core. Okay. So parties inside the goal is that party inside the core, honest party inside core has to make the honest party outside core agree on what on the message that the honest party in core has. Okay. after this happens in round 2, what happens next? If the party is in core, he has to recompute its. He has to reconfigure his jth core word. What does he do? So, if he is in core, his core word is good to go. So that happens, and then he'll generate a witness for that new core word. Or else, what does he do? The party will get a party outside core. He'll receive the tuple and witness from party in core. He'll run the verification algorithm. If it passes, he'll assume whatever is sent is true, and then he'll take that as the correct tuple and correct witness. Right. So at the end of round 2, what is the current state? Every honest party has one verified witness and tuple, right? So round 3 is naturally everyone has to now get the message. Everyone has to agree onto the same message. So what does every party do? Every party basically sends the verified tuple and witness to the party outside core. And now party outside core, what does it do? It gathers all the verified witness and tuples. He runs a verification, and if the verification passes, puts it into a set, and then once t plus 1 parties once he gets t plus 1 tuples, party outside core will interpolate the points from the tuple to form M. So yes, so all honest parties do indeed have M. If you see validity, how do we prove it? Every honest party will start with the same message, and therefore he'll have the same code word, and every honest party will have the same accumulation value. And so since there are t plus 1 honest parties, it will happen that H is a subset of core. So all honest parties are in core, and all honest parties will output N straight away. That's a simple proof. Consistency. So we have to again go back to by on consistency and validity of that broadcast protocol, every honest party will have the same vector of Z values. Okay. Now, if there are n minus t such same Z values, there exists a core, or if not, there exists no core. So what we can what does each honest party have in guarantee? All honest parties agree on whether there is a core exists or no. So core is t plus 1, as I said. So we can be assured that there exists at least one honest party in core who has a message M and corresponding to the common accumulation value Z, who will send the correct tuple and witness. Right? Collision resistance here is will force the component to be equivalent to the message M's component, or else if the correct party indeed does send a bogus value, the verification run at the other end will simply fail there. And you have next you'll have to prove that honest party outside core indeed has M. So how do we do? T plus 1 honest parties are there. You remember every honest party sends a verified tuple and witness. T plus 1 are there. So its receiving set will have T plus 1 verified tuple and witness values. So he will be able to interpolate the values and agree on the same M value as the honest party in core. So that's consistency there. Now if you see, the bottleneck is that we are actually, after making the value public, we are running a local computation saying, do we have a core? If so, and then the core party, and then after we know the identity of the core, the core parties compute a witness and send the witness and tuple. Do we actually need that as a question? We can actually collapse the first 2 rounds into one. What we actually say is, you make values public, and at the same time, you compute witness. You proactively compute a witness for each tuple, and then send it across. So have in first round itself do both of them, and local computation you will I'll be able to identify whose score.
Can that second, sending witness components be done without knowing the code?
If, assume no, you don't assume that you are there as core, and then compute the witness and send. Right.
But core identity may not be known.
Core, correct. So core identity will be known. So you send witness and tuple proactively. Everyone sends proactively their witness and tuple, and then the local computation happens where you will finally you will know the identities of the parties in core. Right. So all parties will know who's core. So whoever is there, the components you receive from core, you keep them. The components you receive from who's not in core, just discard them.
But at least you have to wait for every
Asynchronous.
send.
Synchronous. So should be fine.
Okay. Your round second message can be sent only after the first one is available.
That was the previous one. Now I'm saying you compute you are making the accumulation value Z broadcast, and you send the witness comma tuple to right away you compute and send. And then once you form the core, you will know that okay, this tuple and witness belongs to the party in core, or this tuple and witness does not belong to. So if it doesn't belong, you just discard this witness and tuple straight away because he's not in core. And whoever is in core, whoever you know the identity of the core, take his component, and then the rest of the protocol remains the same. So now we have collapsed it into a 2-round with 1 seed round protocol. And that's it.
I have a small question.
Okay.
So I have a very naive approach for doing this agreement, let's say in the cryptographic setting. So let's say all parties have some L-bit inputs. They can just compute hash on their input or some compression function and then just run an agreement protocol. So doesn't that reduce the size and make the cost independent of L?
No, but so you're just saying compute hash and then run agreement on the hash.
Yeah, and if the agreement succeeds, then whatever values the parties have is the thing. Otherwise, they just take some default value. Will that protocol work or?
What is the how many bits you are sending through the read broadcast?
K bits, kappa bits, Z value.
Kappa, how big is
The accumulator.
it? How big is
It is much lesser than n.
it? Much less. I understand.
It is constant size. I mean, it's kappa bits output only you get, right?
I'm asking kappa to defend you. What is the value of kappa? For instance, hash function, if he is saying, right?
That will be like 256.
256 bits.
But I'm just wondering if this protocol has some issue.
But then when different parties start with different inputs and the agreement is on the hash, some value is agreed on, how do you go back and identify what value it is?
Hash is a one-way function, no?
If it's not a value that I started off with, some other honest party's input turns out to be the output, let's say. Then from the hash values, how am I
If in the hash, when parties will have hash value as the input,
yes.
right? If all the honest parties agree on the same input, have the same input, then the hash value will also be same, right?
Yeah,
And then
that will be fine. That is
Yeah, validity
But then if
case
they
it
have-
will work. Validity case it will work.
Ah.
Everyone starts with the same input, everyone has the same output.
exactly.
If they don't start with the same input, you will have, if the trivial output only will be there every time.
Yeah, but you can just assume some default value as the output, right? All honest parties can output some default value.
No, no. So some honest parties start with the value, some other honest parties start with a different value. If the output of the hash values turns out to be the output of some of the honest parties,
Okay.
from their viewpoint, it seems like there is an agreement, right? So they will terminate with their output, whatever the original output is. Now, if you're saying terminate with the default output, the other set will terminate with some default output.
Okay.
But when you won't have agreement,
I see. Okay.
Validity case, it will work very easily.
Okay. No. Thank you.
If there are no other questions,
Okay, now our department chair, Professor Vinod Ganapathy, will address you. He has something to tell you.
You know what's the hardest problem in computer science? You know the answer. USB-C. HDMI, there's no HDMI cable here.
No, there is one.
Oh, there is one. Oh, okay.
Yeah, directly.
You can directly connect.
Okay.
Actually,
Solved.
Yeah.
Still not solved. Okay.
No, I think that switch the.
I have to switch, is it? Okay, now where is the.
Something came. HDMI 1.
It just came and then went away. Okay, good. So, welcome. My name is Vinod Ganapathy. As Professor Arpita mentioned, I'm currently the custodian of the department. So, it's my pleasure to welcome you all. I noticed the name of the workshop is MPC Retreat. Usually, retreats are held in resorts. You are in one such resort, okay? And what's that?
I'm poor people. I'm poor, so
No.
organizing at IISc. And IISc is like a retreat.
That is what I'm saying.
Oh, okay.
That is what I'm saying, right? And it is my pleasure to tell you about the story of this resort, right? So it was founded in 1909, realizing a vision of J.N. Tata. Actually, the story goes that he was on a ship in 1893 on his way from Japan to Vancouver, and on the ship he happened to meet Swami Vivekananda. Okay, and the story goes that he had this vision that India should have its own research institute, and he expressed this vision to Swami Vivekananda. Few years down the line, he actually wrote a letter to Swami Vivekananda, reminding him of this conversation that they had on the ship. Unfortunately, none of them lived to see the day. J.N. Tata passed away, I believe, early 1900s, and Swami Vivekananda also followed suit. But the vision sort of was mentioned to other people, and they took the vision forward at that time. And Tata, of course, donated a large part of his estate to IISc, his wealth, and Swami Vivekananda also played a big role in influencing the erstwhile government to establish this institute. So these two people came together. Of course, you need the land, right, for the resort, and the resort could have been in Jamshedpur, it could have been in Roorkee, but it happened to be here because the third great person on this slide donated the land, and that's the Maharaja of Mysore. And so that's why we are here. This is the story of the institute. My presentation is mostly going to be stories and facts, so pardon me, it's not going to be as interesting as some of the other presentations that you have had. So let me now tell you about the story of our department. Now that I have told you the story of the institute, we are at this point 55 years old, and we are the top ranked department in India based on research output. And we celebrated the Golden Jubilee, or we tried to celebrate the Golden Jubilee in 2019-20, but then COVID got in the way. But we have celebrated. Okay, so here we are. I understand most of you in the audience are students, so I'll have quite a few student-centric things to say. In our department, we do research in the standard 3 streams of computer science. There is a vibrant research group in theory and cryptography, and I'm sure you have all looked up that work that's going on here. There's also very active work going on in computer systems and also in machine learning. Okay, so with that, many of you might be considering futures in graduate study. Our department does have a very active and vibrant PhD program, as well as an MTech by research in computer science and engineering, and the entrance for both is GATE, or if you're from a CFTI institute, there are the standard criteria that are applied, and you just have to apply and come for a research interview. Right? So that's the process by which we select students. Those of you that are undergrads, are there any here? Okay, you are welcome to apply for our MTech in CSE by coursework. The entrance is through GATE. There's also MTech in AI. Those of you that are school students, I assume there are nobody. Okay, the BTech program is also there. Anyway, I also want to tell you about another program that we have in the department. Professor Arpita was the coordinator until last year. Many of you might be considering careers in research, but might not be sure about it, right? Before you commit, you want to sort of try it out. And our department has this program called Sparks. It's not a formal program like a degree program. It's what is, come to be called in the industry as a pre-doc program, right? So we call it Sparks, Scholars Pursuing Advanced Research in Computer Science. We have a periodic call. I think I took the screenshot from the most recent call, 30th September. From time to time, we have a call, generally twice a year, and you're welcome to apply. Generally, the selection process here doesn't happen from the department, but rather individual faculty members who look at your profile and see if you're interested. And you are welcome to come join us for a year, 2 years, do some research, hopefully get some output, and then see if you like it. Okay, that's the general goal for the program, and we have around 10 to 15 such Spark scholars that are part of the department. They've come, many have moved on, but this is something that we welcome your applications to, right? I mean, if you're interested, I'm happy to answer questions. I think Professor Arpita is also very familiar with this program. She can also answer questions about this. Of course, you can choose from any one of 25 faculty members in the department that pursue work here to sort of work on your Sparks program, right? So this is just an overview of where the faculty came from and the various areas that they work in. Okay, there is a +1. That +1 is a faculty member who I will not reveal right now. He's joining next year in January.
Next year?
In January, he's joining in, but he will be here from May onwards. Let that be a secret. Okay, so very happy in some sense to present this slide. People generally ask, how is research in India versus research abroad? And if you were to look at the history of the department, right, until around 2016, it was the case that, roughly I'm just saying, it was the case that, getting a paper at a top venue from an Indian institution was a big deal, right? And very proud that this department has been the in some sense, the inaugural publisher at many top venues. But 2016 to 25, we have had the good fortune that, this has become a routine occurrence, right? And every one of the acronyms you see on this slide represents a venue in which there has been at least one paper from this department over the last 10 years, now 11 at this point. And we have moved on from just publishing here to seeking grander goals, things like most influential paper awards and so on. Hopefully, the work will have impact. It takes time to have impact, and that's what this slide shows. So, if you were to become a student, you'll become part of this gang here. So, there are around 100 PhD students in the department, around 25 MTech by research students, and 160 MTech coursework students, right? This data is slightly old. I don't have data from last year, but it's roughly the same. The trend sort of continues. And of course, we are very proud of all of our students here. They have gone on to do great things. Almost every year, our department has been fortunate to receive or be a runner-up in the ACM India Best Doctoral Dissertation Award competition ever since it started in 2017. And there are a number of really stellar graduates that have gone on from our department to top places in academia worldwide, top industry locations worldwide, and so on. And you can just see a sampling of some of these alumni here. We do have very active industry collaboration. These are just a few examples. Walmart, ETM, and Sonata have all endowed fairly large grants to the department. So these things end up funding things like travel, machines that students can work on, and so on. Okay, including this room. Okay, this room was funded by one of these initiatives, and there is a little secret about this room. How many of you know it or have?
I told them to look at this.
Okay, so this was where Wipro was incubated. This room right here. Almost 50 years ago now, right? So Wipro's IT wing, I mean, Wipro was a company even before 1979, but they incubated their IT wing over here. There are several other sort of large companies that have born out of this department. So that culture also exists, the entrepreneurial culture, if you're interested in that. Now, how do you engage with industry? For example, you might be interested in taking your research to the next step in industry. The department does encourage this, and this is not a departmental thing, it's actually an institute thing. So you are allowed 6 months of internship as a student if you come here anywhere in industry or at another university. It can be increased to 12 months if it is directly related to your thesis, for example. And it can even be increased to 18 months if there is some sort of an agreement between the institute and wherever you're pursuing your internship. And as an MTech student, it's a more limited internship period that you can do, 3 months, but it has generally led to productive collaborations, even that small duration, outside of the institute. Okay, so that's it. I don't have any more to say. If you have questions, I'm happy to answer. And I would like to say welcome, but I think we are near the end of the workshop. So any questions, I'm happy to answer. Okay. Otherwise, have a good rest of the workshop. I think today, one more session in the afternoon?
Yeah.
Okay. Cool. And keep your eyes open. There are many other workshops that the department organizes throughout the year. You might be interested in other topics. Also, just keep an eye out on our webpage, and you're welcome to apply to all of these programs. Okay, thank you.
Yeah, please join us. Am I audible?
Long press there.
Long press. This one. Long press. Hello? Yeah. I think there's still
1 more minute.
yeah, two more minutes. And the slide change is here. Yeah.
So it is my pleasure to introduce Professor Arpita Patra. Arpita Patra is a professor of computer science at IISc. Her research focuses on cryptography with particular emphasis on the theoretical foundations and practical implementations of secure computation protocols. She has authored over 100 publications and her work has been recognized through numerous honors, including the Professor S.K. Chatterjee Award for Outstanding Woman Researcher/Industry Leader, the Google Privacy Research Faculty Award, the J.P. Morgan Chase Faculty Award, the Sony Faculty Innovation Award, the Google Research Award, the NASI Young Scientist Platinum Jubilee Award, the SERB Women Excellence Award, and the INAE Young Engineer Award. She is affiliated with leading scientific academies, including the Indian Academy of Sciences, the Indian National Academy of Engineering, and the World Academy of Sciences. She has co-authored 2 academic textbooks, Secure Multiparty Computation Against Passive Adversaries and Fault-Tolerant Distributed Consensus in Synchronous Networks. Beyond academia, she conceived Expedition Aparajita, an initiative celebrating raw human will, particularly that of women, through extreme endurance challenges. As part of this expedition, she is pursuing the ascent of the highest volcanic and highest peaks across all 7 continents, with 5 volcanic peaks and 3 peaks already completed. She conditions her body and mind for these expeditions through marathon running, long-distance swimming, and extended cycling. Today, she will talk to us about the landscape of exact round complexity in secure multi-party computation. Please put your hands together to welcome Professor Arpita Patra.
Thank you, Ashwarya. Okay, so I'm audible, right? So the round complexity is the topic of today. We planned, as a series of 3 lectures, but unfortunately, the remaining talks are cancelled. So the ward situation has not just impacted the dosa and roti consumption in India, but it also have left footprints in this tiny conference that we are having here. So the plan was that I'm going to give the landscape. I'm going to paint the landscape of the area, and Benny and Eliran, they're supposed to give more details, but unfortunately that party will be missing. But maybe for some other events, I'm going to invite them, hopefully physically, to India, and then we'll have the talks at a later point of time. So since this is going to be a overview kind of a talk, so expect a lot of results. So be patient, and whatever you have learned so far, listen, class out for now, because I need your memory. Okay, so I'm going to go very, very slow, and like everybody in the speaker in the workshop iterated, stop me at any time with any questions. Okay, and at some point of time I have some questions for you, and unless at least one person who are not part, of course, the part of the course that I'm running this semester answers my question, I'm not going to go forward. I want that answer. Okay, and I can actually randomly pick from the audience. So that'll be a check that you are listening to me or not. Alright, so with that introduction, let's start. So this talk is actually the series of 3 talks was supposed to be based on a bunch of works that you see on this slide, which are done between 2020 and 2023. 3 years we had been extremely productive. You can see the papers starting from Fox 20, then TCC 20, Crypto 21, 22, 22 again, TCC 22 and Stock 23. In fact, the TCC papers are a result of the fact that we had, we have the results in the middle of the year. And those of you who are researchers already in crypto, you know the deadlines, right? Crypto is towards the beginning of the year, February, and Eurocrypto is in October. And in between we have got the results, so we could not wait. So that results are still good, really good quality results. So thanks to all my co-authors, Benny and Eleven, of course, who were supposed to give the talks. And apart from that, we have Akshay and then Or and you all. Thanks to all of them. Right. So what is this talk about? So this talk is about the round complexity of multi-party computation. So round complexity is one of the important complexity measures. So yesterday was mostly about communication complexity, right? What is the communication complexity? What have you learned from yesterday? Communication complexity of any interactive protocols. Anybody?
Amount of information that needs to be sent around.
The amount of information, typically we measure it in terms of bits, right? In terms of bits. So there are these parties, and we are talking about interactive protocols, meaning that the parties are talking to each other, and therefore they need to talk to each other. They don't talk like this. I mean, they probably can talk like this, but everything is translated to bits in digital systems. So we are measuring communication complexity in terms of bits, right? How much bits are put on the channels, the TCP/IP channels, whatever, over which we are communicating. Right? That is what we had been concerned about yesterday. And today's concern is round complexity. It is easy to mingle these two complexities, but they are separate. Okay? By round complexity, I mean how many times the parties are talking to each other. How many times the parties are opening their mouth. Once you open your mouth, you can speak as much as you want. You can spit out as many bits as you want, right? But the number of times you are opening your mouth to speak, that is intuitively is counted as a round complexity, right? So when I count round complexity of an interactive protocol, I assume that the protocol is running in steps, okay? And each step is actually called a round, and in that one, the parties are talking to each other, right? And talking to each other is not like many times. They just talk. Everybody is speaking to everybody else, and everybody is collecting what everybody has spoken to them, and then they are doing a local computation and getting ready for the next round. Next round, and they are going to repeat the same thing. They are going to again whatever they have computed, they are sending to other parties, collecting what the others spoke to them, and doing a local computation, right? Sending, receiving, and then local computation. These are the 3 things that are happening in one round, right? And what I want to count is the number of rounds needed by an MPC protocol, right? Of course, I mean, you can need any, and you can, your protocol can require many number of rounds. What I am interested in is that what is the minimum, what is the optimal number of rounds we need to achieve certain tasks in MPC. So that is the fundamental question that we are interested in or concerned about,
right? And we will try to answer that. So yeah, so basically that's it. That is the introduction, and this has been one of the most fundamental complexity measures for any interactive protocol, including multi-party computation, and a lot of effort has been put over the years for analyzing the round complexity of MPC protocols, and we will review some of them very soon. Okay, so I guess at this point it's redundant to define the problem, but since I have asked you to flash out your memory, so I will tell you the definition again, because you would have probably flashed out the definition of, or you were going to ask me, what is MPC? We have not even heard about it, right? So anyway, so MPC essentially allows a bunch of distrusting data owners to compute some function of their input, of their interest on their private inputs in a way that nothing beyond the function output is leaked, right? So we do have this n parties who are geographically apart, they don't trust each other, everybody has their own input, and the distrust is modeled by a centralized adversary who can corrupt some of the parties. And honest parties have no clue about who the corrupt parties are, right? And we do need two properties. One is correctness. We want to compute the function output. That's the goal. And if you just have the correctness property, then MPC is trivial. But so to make the problem non-trivial, we have privacy, which means that apart from the output, nothing must be leaked. Security. This is actually a very technical concept here, but I'll try to make it as simple as I can. So the security is defined by looking at the view of the adversary in a protocol. Let's say you design an MPC protocol and you are running amongst the parties, and you will look at the view of the corrupt parties, the parties which are under the control of the adversary. Did I say that the adversary is centralized already? The adversary is centralized. That means there is one single guy who is doing all the bad things. It is corrupting some of the parties, and through those corrupt parties it will try to do something wrong, right? So now you look at the view of the adversary, and what we want is that if your protocol is good, we want the view of the adversary to be simulatable in some sense, right, from the input and output of the corrupt parties. Okay, so a little bit in detail, in order to define the security, so we actually define the security of a protocol that you would run in real life by introducing something or imagining something that is called as ideal world. What is an ideal world? It's actually the simplest, smartest, and the cleanest, and what more? And the idealized way of solving the problem. Right? So wherein, of course, you have the parties who want to do multi-party computation with their inputs ready. Right? Apart from that, there is an entity called trusted third party. Right? That's me here. So in that solution, what do you do in the ideal solution? The parties will simply send their inputs to the trusted third party, and the trusted third party, on having the inputs on clear and on knowing the function to be computed, it can just compute the function on those inputs and get the output and send the output back to all the parties. Right? Don't you think this is the smartest and simplest solution that can ever happen for an MPC? So this is actually called the ideal world, right? The most idealized way of solving the MPC, right? Now, what we do is that we compare the real world where we have designed our protocol and deployed it amongst the parties with the protocol in the ideal world. Or in other words, we compare the view of the adversary in the real world and the ideal world. Okay? So, fix your inputs. Fix the inputs of the parties. Run a real world protocol, right? The protocol that you have designed, for which we want to define the security. Right? Run it on the inputs in the real world. Similarly, run the ideal world protocol on the same inputs. Now fix a corruption case. Let's assume that those two parties are corrupt in both the worlds, right? So over there, They would see something in the as a part of the protocol. What would they see? Yeah, their input. They would have used some randomness as a part of the protocol, that, and then what more? Function. Function output. Yeah, for sure. And what else? It's a protocol, right? So there are back and forth. So the protocol would have specified do this, do that, do this, do that, right? So there are many such steps round by round, right? So according to that, they would have interacted with each other. So these corrupt parties would have seen some communication from the other party. So that also they have seen, right? What about here? Same corruption case, same input set. What they have seen here? Input and output, right? In the ideal world, look, there is no randomness, nothing. It's just their input, and they would have received back their output, right? So, if you look at the view of the adversary in these two worlds, right? What we want to say to claim that your protocol is good? What does your common sense say? What do you want to claim? When will you say that your protocol is good?
Even the parties are corrupted, then after that also any point will leave.
Yeah. So what does that mean? So I have actually given you the view of the corrupt parties in the real world and ideal world. What do you want to say to claim that the real world protocol is a good protocol? They should be similar, right? So what does it mean?
They should have the same
Similar, yeah. They should have
the same view.
same view, though not possible, right? Because here these parties are seeing just the input and output, and there, apart from the input and output, they will be eventually able to see. I mean, input of course they start with, and output is what they're computing. But in between, they're seeing a lot of things as a part of the protocol participation. What about that? I mean, that's additional things, right?
The adversary should be able to create.
Yeah, that will be coming as a next step. But if I have that view and if I have this view, what do you want to say? What should be the relation between these two views, so that you can claim that the protocol is not bad. It's as good as the ideal world. The one thing that I probably didn't tell you is that the ideal world is actually, it's a secure solution, because this exactly captures the goal of the multi-party computation. Right? In the previous slide, I said that nothing beyond the output should be leaked. Right? So this is exactly what is captured here, because here the corrupt parties are seeing exactly the input and output, and nothing more. So in order to claim that your real protocol, the protocol that you have designed, is as good as the ideal world, you want to say that the view of the adversary in the real world is not leaking any more information than the adversary, the view of the adversary that is created in the ideal world, right? So that should not be leaking more information than this, right? So that's actually exactly how we define the security. But I think this is more of basics of MPC. We are not going to need that, but you understood what we mean by the security, right? Okay, fine. This is needed actually for the next slide. This is where my first question will come. Okay, so we understood what MPC is. Now going back to what I am here for, to analyze the round complexity, right? So we want to ask questions like, how many times the parties need to talk to each other to get some task done, right? So what is the thing we will start with? We will start with 0 rounds. 0 rounds means the parties are not talking to each other at all, right? So they're just sitting in different islands and with their own inputs, and in the end they're hoping that they will be getting the output of the function. Is that going to happen? No, right? How will it happen? If you are just sitting in different places with your own inputs and you want to compute a function on the inputs of yours, the joint input of yours, and you want to get the output, that's not going to happen. You need to talk to each other, right? At least once. So we'll start with 1 round MPC. So what can you do in 1 round? So what is the structure of a 1 round protocol? Everybody will have their own input, their randomness, right? And they are allowed to speak just once. So they will do some local computation and then they will have something to send to every other party. They will do that and every party will simply receive whatever they are supposed to receive from others. They are supposed to do a local computation and at the end of that local computation they are supposed to get the output of the function. That will be the structure of a one round product. Now you can already see that in the title I've written one round impossibility. So that's already a clue for you, right? So one round MPC is impossible. I'm not bringing in special features of MPC like whether it is against an adversary who has unbounded power or bounded power, whether the network is synchronous, asynchronous. I'm not talking about anything about that. Irrespective of whatever you want to assume, whatever is the most favorite adversary you have, whether it is computationally bounded, whether you like computational security or information theoretic security, it doesn't matter. You can assume whatever you want to assume. My claim is that one round MPC is impossible. Now, what is your duty? To come up with the proof. And basically I explained the previous slide, right? I took 5 minutes probably to just explain that because I wanted to come up with the proof. It's not hard, it's easy. So I want anybody from the audience, barring those who are taking my MPC course this semester. So why one round MPC is impossible to achieve? One round MPC, I have given you the structure, right? General structure. I'm saying any one round MPC is impossible to achieve. Why is that? There is some blah blah stuff is written there. Forget about it. You will come up with what it means actually. Why is it impossible? Anybody? Barring blah blah blah. Yeah. So, who can give me the answer? You want me to pick randomly?
In one round, we have a one round to send the data, and then like in ideal world we have just speak to you give the example like we in one round just speak to once. So if you just give the data to the TTP, then TTP compute something, but we want the output, then we need to talk again to a TTP, like need to communicate with TTP again.
Why? No.
No, not receiving the output.
That a TTP knows its job. It's a TTP. So once it gets the input, then it computes the function, it gives the output. You don't need to talk. You just wait. After you send your input to the TTP, you just wait for the output.
Then we will get the output, then protocol will work. So this is the one round. I think we give the input.
No. So I'm saying that your protocol is not using TTP. TTP is the idealized, smartest and simplest solution, but that's not something that you can use in the real world. That's an idealized solution, right? Because it makes some trust assumption, right? That there exists a TTP. And we are MPC researchers. Our goal is to not employ any TTP and run an interactive protocol or design an interactive protocol that has to be run amongst the parties without the TTP. There will be no TTP in the real world.
Then it's not possible because we have to communicate with each other for computing some.
Why is that not possible?
So you just say x1, x2 and x3, it could be different because it's adversary computer. It will not be the same throughout the protocol, so it could have different function for basically the view will be different.
No, I didn't get it. Come again.
F of x1, x2, x3, x4.
Yes.
X2, the x3
And what are you pointing to? The real world, ideal world, or you're not pointing to anything?
No. Okay, in real world, okay.
Yeah.
You can say the function output could, like the adversary could have he could send some value to someone else and some different value to someone else.
So this is true even for passive adversary. If you are thinking about active malicious, it's not needed. And my claim is true even for passive adversary. Yeah.
So we know that TTP is not possible in the real world. So in one round MPC, each party just sends one thing and receives one thing, so it's equivalent to a TTP mechanism. So that's why it's not possible.
Okay. I don't think that is an argument for an impossibility. You have to show an attack, right?
Yes,
Some breach, privacy breach. That, okay, so take this as a clue, right? So you have to come up with an attack with the adversary, which is possible in the real world but not possible in the ideal world.
So ma'am, if you have just one round, then probably in order to compute anything like one of the party will have to give the exact input to the other party in the real world, which is a breach.
Why? Why my protocol has to be like this?
Because you need to have that exact input.
Huh?
You need to have the exact input from all the parties.
I can compute something on the input. I did not give the inputs just on clear to other parties. I mean, that's your problem. You are coming up with such a protocol, right? But why in one run protocol has to do that?
You won't get all the information required to be able to compute the function and get the output.
Why? If I define a one run protocol, if I say that I have a one run protocol, that is supposed to do that. But do you have a proof why in one run protocol? Yeah.
If some corrupt party claims that I don't get the info, then someone has to send again.
Corrupt party?
It claims that I don't get the input from other parties. So
Why will you not get? It can be a synchronous network, so everybody is sending it, so they will get it. It's a semi-honest protocol, so you have the adversary is passive in the sense that it's following the protocol. So everybody is sending to everybody else. So there's no network failure or anything. It's an ideal. You know the solution.
I attended your talk.
Oh, okay. That's why you're smiling. Okay. To give the answer, I have to move forward. There are a lot of things to talk about.
Okay, so what if can the adversary based on the values set by the honest parties can make his function output? That's basically extra information, and so he can.
Okay, come again. What is extra information and where in the real world?
Yeah, in the real world, he'll see the adversary can see the honest party inputs and based.
Why do the corrupt parties will be able to see the honest parties input in the real world? Why?
I want to say the function output can be without having to actually evaluate. You can produce match the output that is required. I wanted to say that f value should it can change according to the honest party inputs. Is what I wanted to say.
I didn't get it fully. Anybody else?
So just considering the let's say party case and so P1 has x1, P2 has x2. They are trying to compute if x1 x2. So P1 sends some message, let's say M, and by just looking at the message M and x2, it will be able to compute f x1 x2. So so in trusted third party, so in ideal world, you need to simulate the message M, right?
Okay.
So intuitively it seems like M needs to have information about x1. It needs to have.
It will have information. It is dependent on that because M1 is a function of x1. But that's fine. Then you are saying that any even two-round protocol will also not be fine, right? I mean, if you see both the messages coming from this party P1, you are saying that completely. See, that doesn't give without even giving information about x1 that can help me to compute the output. So that's not a contradiction. Why are you not getting it? It's so simple. It's extremely simple actually. Anybody last attempt, otherwise I'll ask somebody else who know, and I know that they know.
So if you try to do that, I think
Try to do what?
like in one round MPC.
Yes.
Then at least one of the honest party will leak the input that it has.
You have some protocol in your mind with respect to which you are saying this? Why it has to happen? I don't understand. Why? Why one of the honest parties input will leak? Okay, so I'll tell you finally the solution. I have to, because it looks like an impasse. I won't be able to give my talk if I wait for you to come up with the answer. Okay, so the problem is, and actually I'm a bit disappointed. I just asked the same question. I didn't give this talk or something else in Chile last week. And there are also people who are very similar background. They don't know much about MPC. I've introduced everything to them. One of the others, there were some 10 people, and out of them, 2 of them actually came up with this answer. So I'm disappointed. Okay, so the attack is as follows. Imagine any one-round protocol, right? I'm running it in the real world. So now if you, so you're running it, okay, with whatever inputs the parties has and whatever the protocol asks the parties to do, they're running it. Nobody is active. Everybody is passive, nice. They are just following the protocol. After that protocol is over, just one round, right? One round protocol is over. Now the corrupt parties, assume the same 2 parties are corrupt, right? So they go back home with their view of the protocol. They go back, and there they try to do, so they fix the messages. So I mean, when they go back, of course they have the messages that they have received from the honest parties. That's the part of their view, right? The one single round, the other honest parties would have sent them something. So that they take home, and now at home they change their own inputs, right, and recompute their message, and then this, in their head they rerun the protocol with different input of theirs, right? Now they should be able to compute what? A function on inputs x1 and x4, which are actually the inputs of the honest parties, but now they have recomputed their own messages based on some x2 prime and x3 prime. So they should be able to compute at home a function on a different set of inputs that they had actually done with the honest parties. The honest parties have got just one function output, which is f of x1, x4, x2, and x1, x2, x3, and x4. But back home, the adversary is getting more, which is evaluation of the function value at different set of inputs, where the inputs of the honest parties are fixed, but the corrupt parties are free to choose anything on their behalf. Right?
Same as the hash one round.
Yeah. So that is something not permitted, or it's not possible in the ideal world. Because in the ideal world, the parties are simply sending their inputs to the TTP. The TTP is computing the function output on whatever is the set of inputs which has been communicated, right? And giving back the output to the other parties. So in the ideal world, they will learn just one function output, basically corresponding to the input set which has been sent by the parties to the TTP, right? So over there, multiple function evaluations are possible. Over here, just one, right? So that is the additional leakage that is happening because of the one round protocol. It will not happen for a two round protocol. In two round protocol you cannot do that, because in the second round also the honest parties are sending something which is based on the messages of the corrupt parties to the honest parties, right? So that is why it's a feature of a one round protocol. And that is called, this sort of attack is called a residual attack, because where you are actually fixing the inputs of the honest parties, you means you are the adversary, you are fixing the inputs of the honest parties, you don't know what they are, but then you can play around with the inputs of yours, and for all such combinations you are allowed to get the function out. So this is, because of this simple reason, one round MPC is impossible.
For generic functionalities.
Yes, for generic functions, right? So all will be for generic functions. There will be some function for which you cannot do it. Yeah. Now one round is impossible. So what would you try?
But the adversary can't get the other honest party's input here.
It doesn't matter. As long as you can claim that the real world protocol is leaking more than the ideal one, it's a breach. You are stick to the same point as before, like in the crypto class. He wants. Yeah, so basically this is why I took so much effort to define the security, right? So in the real world, meaning that where you are designing the protocol and deploying it, if it leaks anything more than the ideal world, that's a breach, right? So in that way it is a breach, and it can actually lead to it can have a lot of implications, but let's not go into the details. It has leaked more information than the ideal one. Okay, now let's talk about two rounds. So what can you do in two rounds? And suddenly the answer is that you can do everything in two rounds. One round is impossible. You probably were not expecting this. Two round gives you everything. So we have two worlds here, and I'm actually still sticking to honest but curious case. So by now you know what is semi-honest and what is malicious, right? So first we are talking about honest but curious. So we have two worlds, honest majority and dishonest majority. And as you have seen yesterday, I guess, I don't remember about first day, but yesterday you have seen that in honest majority world you actually can get very nice protocols which are called information theoretic, where you can assume the adversary has unbounded power, right? Whereas in dishonest majority you cannot get information theoretic security, you need to rely on cryptography. Okay, so we have these two worlds, and irrespective of where you are, we know that MPC can be achieved in two rounds. Unfortunately, of both the protocols, I mean, as you can guess, two rounds we are doing it, they are really complicated protocols. And in spite of this being sort of popular in the community that two round protocol may exist, but it took this many years. So the MPC has started in 1982. Since then, how many years? Like close to 40 years, right? Took 40 years almost to come up with first two round protocols, right? And magically 2018 is it looked like the year of ground complexity. So you can see that in all the results are actually they came out in 2018, and actually these two results got best paper award in Eurocrypt. Okay. So as I said, both are for semi-honest, but this is where it stands. Okay. Now let's see what we have done. Seems like okay, everything is settled. One round is impossible. Two round we can get it. So what are we doing? So we move basically to the malicious one. Seems like semi-honest everything is settled. So we go for the malicious world, and there we consider basically all the fundamental and classic settings, and we resolve the round complexity. So now I'm going to go over 4 fundamental settings. So and just be very careful. There are differences, but they are all fundamental, very classic settings actually. I mean, they are not like ABC or settings. So these are the settings where people have spent quite a bit of time on each of the settings. The first one is
just one question.
Yeah.
2016 also, I guess there were some results for two round at MPC, multi-key FHE based on that. In In 2018, they have this from one-way function. They
No, from obvious transfer,
yeah,
the
obvious
minimal assumption. Yeah, so I care about the assumption as well in cryptography. I mean, of course, if you use very, very strong assumptions, then you can get it.
FHE is like realizable.
No,
But yeah, but
it's still not as good as obvious transfer. We can.
yeah, in terms of feasibility, maybe like.
Yeah, but assumption.
Yeah,
Sure. Okay, so the first is the cleanest setting, perfect security setting, right? So over here you have again a bunch of parties, and typically when I say a setting, there are two orthogonal dimensions that will fix the setting. One is the network, the other one is the adversary setting, right? So network wise, the parties are connected over secure and authenticated point-to-point channels. So yeah, you can assume that let's say this TCP/IP, they are connected over internet, for instance, like TCP/IP. And then there is a broadcast channel available. This is not an extra assumption. Broadcast channel can be emulated given just the basic, secure and authenticated point-to-point channels. So, but for simplicity, we'll assume that there is a broadcast channel. What about the adversary? The adversary has unbounded power, and it's an active adversary. Like I said, it's a malicious domain. So this is the classic setting of BGW, Benor, Goldwasser, and Wigderson, coming from Stockman and Naked, right? So they show a very beautiful foundational feasibility result, which says that any function f can be computed with perfect security in the presence of t less than n by 3 malicious corruptions, right? So if you have an unbounded powerful malicious adversary, then you need less than 1/3 of the parties to be corrupted. Then only you can achieve perfect security. Perfect means no error, perfect, right? There's no error in privacy, no error in correctness. It's a clean model. So this is the first model that we consider. And the second model is the variant of perfect security in the information theoretic world, which is called statistical security, where there is an error permitted either in correctness or in privacy. Most of the time we don't permit any error in privacy, mostly it is in correctness, but definition wise error can be permitted in correctness as well as privacy. And full security means guaranteed output delivery or robustness, meaning that no matter how the adversary behaves, all the honest parties are going to get the output. That's what full security means. Okay, and so in both, I guess the previous one was also full, perfect full security and statistical full security is one. And this is something that you can achieve with the thresholds. So the moment we ask for statistical security, you see a very nice change over here, that you can do the same task as before, but with much lower, higher resilience, right? That is, any function can be computed with statistical security in the presence of t less than n by 2. So this is just honest majority one, because t is the number of corruptions, n is the total number of parties, and we are saying as long as less than half of the parties are corrupt, we can do. The previous one is called super honest majority, because the number of corruptions permitted is strictly less than n by 3. So this essentially, this result is the first result to show the benefit of making errors. If you are happy to make little error, then you get this benefit. You can tolerate more parties. So this will be our second setting. Third one is as expected. So we are now lowering, the power of the adversary. We are making now the adversary polynomial compute power. Right? So we are happy to rely on cryptography. In the previous two settings, there information theoretic, adversary has unbounded power. Therefore, no cryptography can be used. But here, when we assume the adversary is polynomially bounded, we can rely on cryptography, but we want to restrict the use of cryptography. We want to use, yesterday you have been hearing a lot about lightweight. right? So we want to restrict to lightweight cryptography, meaning that only symmetric key is permitted. Everything, so we want to rely on assumptions which are equivalent to one-way functions, the very basic assumptions that is possible in cryptography, right? That is permitted. And so computational full security, even here we need t less than n by 2. Okay, this is the third setting. And what are you expecting as the last setting, the fourth one, and that will be the last one. Of course, it is going to be the dishonest majority setting. So far we had been in the honest majority, super honest majority and everything, but now we are allowing the adversary, of course, to be computationally bounded, and we want to go all the way and tolerate the strongest kind of adversary, which is dishonest majority, right? So t less than n. And for such world, right, the dishonest majority world, we cannot still rely on one-way functions. It is a famous result from known in MPC, where it's known that you need to rely on a primitive which is called oblivious transfer or more. Oblivious transfer is the minimum assumption that you need to rely on to build a protocol in the dishonest majority setting. Okay, and this is why we stick to oblivious transfer, because that's a minimal assumption you need. Right? You could study round complexity relying on, like you were saying, right, strong primitives like FHE or something more, functional encryption, or even those which are higher in hierarchy. But I think from the theoretical standpoint, it is the most important question to ask how many rounds are needed when MPC is relying on the minimal assumption that is needed, right? So oblivious transfer is the minimal thing that you need. Okay, and you can see that there is a change. We have moved from full security to abort security. This is not by our choice, but we were forced, because again there is an impossibility result that shows that in the dishonest majority setting, fairness or so the guaranteed output delivery, forget about fairness, I don't want to bring that. Guaranteed output delivery or full security is impossible to achieve. What is full security again? Which means that no matter how the adversary behaves, all honest parties will get the output. That is robustness. That is something you will not get. You will not get, no matter what. You cannot design a protocol which will have guaranteed output delivery in the dishonest majority setting. So that's why you have to give up with that property. So we have computational abort security. So these are the network, so these are the settings or regimes in which we study the round complexity. Is that clear, all the 4 settings? Yeah.
So how does oblivious transfer the minimal assumption?
How? So this has been proven. So what it means I can tell you, and how is a big answer that I can't give you. So this is proven. So basically it has been shown is that oblivious transfer is complete for MPC, which means that if I give you oblivious transfer as a magical box, apart from that you don't need any cryptographic assumptions to build an MPC protocol. We know how to build information theoretic MPC protocol even in the dishonest majority setting, given this oblivious transfer, right? So that means that whatever assumption you need to build an oblivious transfer, that is all you need. Outside the oblivious transfer, you don't need any cryptographic assumption. They can be information theoretically secure.
So you can realize any basic circuit using OT. So that's it. Then you can compile them to build a protocol.
But oblivious transfer is something that you can't build from one-way functions and information theoretically. You need cryptography, specifically some public key assumptions to build oblivious transfer. Right? So that's what it means. Complete means that that's all you need. Apart from that, no cryptographic assumptions are needed to build an MPC protocol. And you don't need anything else. No other cryptographic assumption. You just need to believe that oblivious transfer exists in this world. Right? That's all. So these are the 4 regimes where we have round complexity results. I'll come to the results, but do you have any questions for the 4 regimes or models that I have defined so far? Yes. So full security means that the protocol is capable of delivering output to all honest parties in spite of how the corrupt parties behave. So adversary is malicious, right? So it can force the corrupt parties to behave in any arbitrary way, right? It may not follow the protocol, it can do whatever junk things it wants, but despite that, the protocol is such that if the protocol provides full security, it is such that honest parties will get the output. Yeah, it doesn't matter, yeah. It's a qualitative property of a protocol, right? So if you are claiming that your protocol is full secure, then that's what the protocol achieves. It's a definition, yeah. Now whether that is possible to achieve or not, and in what setting, that's what I said, that if you have honest majority, only then you can actually get fairness, full security, right? Otherwise you cannot. Abort is the other extreme, which means that the adversary has the capability. Your protocol doesn't give full security, which means that in the end of the protocol, the honest parties will either get the output or it will get nothing, and it will know that it has not got the output. No, that's not possible. So either the correct output or it gets something called bot, a special symbol, which indicates that it has not got the output. And terminate. It has to terminate. Can you be a little louder in my malicious case?
So if a malicious party does not even use up the correct input, then how can you guarantee correct output?
So what is the meaning of correct input?
Let's say they just have to compute x1 plus x2 plus x3 plus x4, and a malicious party does not even use x2. It just use something else.
So for malicious protocols, right? So we as a part of the protocol specification, it is also specified from what domain or from what set the inputs will belong to, right? Now an adversary can use any of this, right? And if it uses one particular input and it is consistent with respect to that input, then it is fine. We will take that as its input. But the initial choice is up to it, right? It can choose anything.
But it has to stick to it.
It has to stick to it. So if it does not, then your malicious protocol takes care of it. It somehow identifies that it does something wrong, and then you discard that part.
So you can error correct.
It's not error correcting. If it is like inconsistent in terms of giving inputs, then typically your protocol, malicious protocol, will be equipped with some steps which will make some correcting measure in terms of either discarding or whatever. Yeah.
If you allow like in n-1 corruption, so if all the parties choose, like all the dishonest parties choose not to send anything, then there in the honest majority you can choose like, okay, if I get n-t outputs will proceed, but here how can you do, even if it's just normal sum?
How can you do with what?
Like you can't do anything, like the all like you need some time bound, put some time bound.
Yeah, so this is the whole thing about the round complexities. It's the rounds, right?
No, there your condition is you wait for until you get n-t out.
No, that is asynchronous. This is synchronous.
Oh, okay, sorry.
Yeah.
Sorry.
Okay, so four settings are clear, right? Now let's move on. So I will first have a little bit of the literature, what is known, and the next slide onwards will be what we have done, what we have contributed. So of course there are a lot of results, and I won't be touching everything. I'm going to touch only the ones which are necessary. So the first column is about recalling the ancient protocols, right? So this is a sort of summary of the previous slides. So if we go back to BGW88 or CCD88, they show that every function can be perfectly computed when t is less than n by 3, right? And this is optimal. You cannot do better. And in the subsequent work of RB89, they have shown that if you relax perfect to statistical, that is with error, then you can do MPC with t less than n by 2. Now if you look at the round complexity of these protocols, they are actually many. In fact, they are linearly dependent with the depth of the circuit of the function that they want to compute, right? So there's a little bit of background. The way we solve MPC is by, for any function, is by representing the function as a circuit. You could choose your favorite circuit, whether it is arithmetic or Boolean, doesn't matter. Now the round complexity of these protocols is actually linear in the depth of the arithmetic circuit representation of the function. They are not constant, they are depth dependent. Okay. Now the first time we got to know about constant round protocols is actually after 2000. So there was a very beautiful result which was given by IISc, Yuval Desai and Yal Kusilovich, where they show that any function can be encoded as a low degree function, right? So your original function can have any degree, right? What they show is that any function that you have, you can transform. Even before you start running an MPC protocol, you can transform your function to a low degree function. To be very specific, they have actually shown how to represent a function using degree 3 function. Okay? And now if you evaluate this degree 3 function using all these previous BGW, CCD or RB protocols, they are going to give you constant round protocol, because you have transformed any function which can have, let's say, degree D depth, R is already transformed to a function which has depth constant, and that if you run through the existing protocols, that will give you constant round protocol. So that is what they have shown. The only bad thing about the protocol, this transformation of the function is that it's not efficient for any functions. To be specific, actually if you take constant NC1 circuits, NC0 circuits, right? So logarithmic depth circuits, for them we know, for those the conversion is polynomial time, and therefore this works. So yesterday, I guess in Ivan's talk, there was an open question he left out to study the round complexity for efficient. So that's what it means. Because these constant round protocols are for log space computations. Right. So these are the constant round protocols. We still yet don't know what is the exact constants that are needed. Constant can be like really big, 100 is a constant, right? So we wanted to find out the exact round complexity. And whether it is like we have been asking in the beginning, where 1 round is possible, 2 round is possible. So we want to pinpoint or find out what exactly is the round complexity, whether it is 2, 3 or what. Recently, so this is recent 2018, 29, around that time. So the concept of this transformation or this encoding of functions that I was mentioning, that had been extended for multi-party. Don't need to understand that the differences, but this is yet another type of conversion of the functions to low degree computation. And what has been shown is that every function can be securely reduced to degree 2 instead of degree 3 as before, right? So that has been shown, and because of this transformation, there was a protocol where it is shown that any function can be computed in 3 rounds with perfect security, but with t less than n by 4. Is t less than n by 4 optimal for perfect security? No, right? We just have seen it as t less than n by 3. But anyway, so they have considered the non-optimal resilience case and they have shown that 3 round is possible. Now from here, our results start. So just for you to recall, n is the total number of parties.
Can I go to the previous slide?
Yeah.
Can you explain what is circuit size in terms of gates? Means is the number counts of gates?
Circuits, yeah, number of gates.
And what about the depth of is there a circuit depth?
Yes, multiplicative depth. I mean, if you have a circuit, of course, it will have a size and it will have a depth. Depth is the multiplicative depth. Right? So you can look at the circuit as level by level. All those multiplication gates or addition gates you can do in parallel, they can be put in one level like that. So you will have to count the number of levels. And those protocols had round complexity, which is at least the number of levels that you have in the circuit.
In the middle column, every function securely reduces. What is the meaning of securely reduces?
Which one?
Yeah, the third bullet point.
Yeah, so this is basically you can take the function and you can write it in a different way so that this different representation have only degree 3 terms. Like let's say x1, x2, x3, product of these 3. So this is a degree 3 term, right? And you can represent such that it's like addition, sum of many such degree 3 terms. So that is the result from their paper. How it is done, it's not possible to discuss now, it's an involved paper. But the point that you should take away is that any function that you have that has an equivalent representation where every additive term is of degree at most 3. Okay, now what we have. So the first case is, so full, perfect, all the terms are defined to you now, right? So if you take the case of perfect full security and if you take non-optimal resilience of t less than n by 4, 3 is the number of rounds that is necessary as well as sufficient. And this is shown by the previous work, this is not our work. And the upper bound, you know, the protocol is shown by the previous work. And why is it optimal? Why 3 is optimal for this? It is due to this result of General et al. And they show that you cannot achieve full security in 2 rounds when t is more than 1. T is the number of corruptions. So if you have more than 1 corruption, then full security is impossible in 2 rounds. So that means the 3 is optimal because they are achieving perfect full security, right? And of course the next open question is, so they have looked at with non-optimal resilience. So what about perfect full security with optimal resilience, which is t less than n by 3? This is something that we show in the first paper, Fox, in 2020. So we have both the lower bound as well as the upper bound, right? And we show that 4 is the optimum. So do you see there is a cost that we are paying for malicious adversary? Because when you were in the semi-honest, honest but curious case, everything was done and dusted in 2 rounds. In this slide, you will see that there is nothing we can do in 2 rounds for malicious world. Even though you go for non-optimal resilience, still it was requiring 3, and when you have optimal resilience, then we needed 4. So that is all is that basically settles the perfect security world. Now if you come to statistical security, where you are permitted to do error, and in fact there is benefit of making errors, this is what is the status. If you go for statistical case, remember that honest majority is the optimal bound, t less than n by 2. So we first consider non-optimal case, and the lower bound will be I mean the result is that it requires 3 rounds, and 3 is optimal because of GIKR 02 again, and we give the upper bound. What about the optimal resilience case where we have exactly T less than n by 2? There again we show that 4 is needed. And we needed a lower bound as well here because GIKR will not give you that. So we have a lower bound as well as upper bound, and both are extremely important. So this slide basically summarizes everything for perfect and statistical for malicious case. So 4 is basically you need for optimal resilience. Now I have a slightly different way of presenting it. I think it adds value. So in this case, there's a nice graph there, and over there in y dimension you will see that that's actually the threshold t. At t equals to 1, t is less than n by 4, n by 3, n by 2, like that. And in this x dimension you have the round complexity 2, 3, 4. So because of the JIKR 02 lower bound, you know that you cannot get full security in 2 rounds when t is more than 1, right? So that leaves almost nothing to be done in 2 rounds. What can you do in 2 rounds? What does it leave the possibility for? That lower bound. Can we do anything for 2 rounds? Single corruption. Does anybody care? Somebody was telling about that sort of result on the first day. T equals to 1 and we have a protocol. And they have a paper. But yeah, I mean, just to close the area, we care about t equals to 1, so because that's the only case that is remaining here. So exactly when t equals to 1, then there is a 2-round protocol, and that small gap was closed by IKKP 15. They have given a protocol, 2-round protocol. But apart from that, you can't do anything. And then we have the lower bound, which says that no perfect full security in 3 rounds when t is greater than n by 4. So which means that that case we need 4 rounds. Then we have another lower bound for statistical case, which shows that no statistical full security in 3 rounds with t more than equals to n by 3. So we have that green box. Yeah.
For two-party computation, T could work like this.
Two-party computation, perfect security, I mean information theoretic security will not get, right?
Because it's not.
Yeah. Right. So these are both upper and lower bounds. So now the question is that this three rounds is almost empty, right? So 2 round almost you can't do anything. We have done only for t equals to 1, which is the only feasible case. 4 rounds we could do with the optimal resilience. So that's how actually the non-optimal cases are, some sort of we have justified. 3 rounds there is nothing. So the question is, if we go for non-optimal resilience, can we really do something in 3 rounds? And the answers were yes. So for the perfect case, if you go for non-optimal resilience of n by 4, then you could get a 3-round protocol. And similarly for the statistical case as well. N by 3 is a non-optimal resilience and you could get a protocol. Now I have the open questions. So, there are a lot of open questions. All of them are extremely hard. That's why we have left them. But it is hard for us. We have tried. Doesn't mean that it will be hard for you. So that's why that is the point of putting these open questions. First open question. Both these upper bounds are exponential. It takes exponential in computation. Right? The parties are doing computation. Also communication is exponential in. No, not communication. Only computation. Okay? For both these protocols. So the question is, can we get rid of it? Can we make them polynomial time protocols? So that is and we have actually solved partially this question. In fact, that case and we have moved from perfect or statistical security to something called everlasting security, which is a sort of a hybrid between statistical and computational security. Okay, so everlasting means that we want correctness for computational and the security, the privacy property for unbounded powerful accuracy. If you don't want to hear this, if you want to ignore this for now. It's fine. Everlasting security, if you did not understand. But these two open questions, making them polynomial time in n is both of them are open questions.
So is it because of the conversion from this function to?
No, it's not because of that. That is already there.
Okay.
On top of it.
Oh, on top of it.
Yeah, this is exponential is the number of parties.
Number of parties. Okay.
It's actually, I'll tell you, because it's actually in one place in the protocol we are finding cliques. And click finding, so it's a sort of a graph where there are n nodes corresponding to these n parties, right? And we need to find out a click. Yeah. So we are assuming the parties are having the graph and they are running a local click finding algorithm to do this. Second, more open questions or okay. So yeah, of course I told you it's because of that function expansion. Because of that, all these protocols are for log depth circuits. So of course the natural question is, can we remove that?
Exponential growth.
Yes, yeah. So can we get rid of that? So that we have tried to resolve for the cryptographic protocols, and where we are sort of successful. Not the information, the perfect security protocols, but using cryptography we can do it, right? So yeah, I think so. Instead of that statistical protocol, right? If we rely on one-way functions, now cryptography is injected in, then we can do it for all functions, not just for log depth functions, but all functions. But that's the compromise. Instead of statistical security, we are now relying on one-way functions. And then what we tried is that this is with the resilience t less than n by 3, right? So we have been trying to push the resilience, and we have been trying to make it work even for n by 2. And in our work we had been, this is not really sitting right on n by 2. We could stretch almost there, but not exactly t less than n by 2, right? But for very close, we could actually solve the problem. The same thing, that it works for all functions, but from one-way function. That's the assumption. Actually, injective one-way function, little more than one-way function, but it's fine. And if you know, for that regime, all the existing protocols are based on public key assumptions so far, before our work. And you are probably asking this question, and who cares whether it is public key based or one-way function based? No, we do have to care, right? It's two different ball games. So yesterday, I guess Aniket was giving you some ideas about how much time it takes for one symmetry key operation to be executed and one public key operation to be executed. There's orders of multitude difference. Okay, so we do care about these assumptions. Something which is based on just one-way function, we must value that over something which is based on public key assumptions. Okay, so this was mostly about it. Yeah.
In this computation thing, you give the lower bound as well as the protocol for
Which one?
for the computation.
There are just
t less than n by 3 and t less than
n by 2. These are what, optimal or not?
No, you give a lower bound result and a matching protocol, or it is just the result?
So these both protocols give full security. And when you have a full security, then because of the GIK result, you cannot do it in 2 rounds.
Okay.
So 3 is what is needed.
Oh, okay.
So that lower bound comes from GIKR, we didn't have to give.
Give protocols.
We just have to give the protocols. Yeah, so the lower bounds for these are non-trivial because these are core rounds, right? There is nothing existing to back it up, but for over here these protocols are backed up by GIKR 0 to 12. Okay, so the rest of the talk, I think we have just 15 minutes. Let me see. I mean more than 15 minutes. I should be able to tell you. So what is remaining is the most difficult one. Actually, all of them are difficult. I shouldn't just put it this way that those are easy and these are more difficult. It's not that. All the settings are very, very difficult. But let me focus on the last regime that I have mentioned, that is dishonest majority. Over here, we recall that we can get only abort security. Actually, we can get something more than abort security, but for this talk, fine. Abort security is what you can get. And the minimal assumption is oblivious transfer. So, let's see what is the status here. Right? So, let me first define oblivious transfer, or you know it already. You know it. Right? So it's a two-party primitive, and that's the magical box. The sender gives 2 inputs and the receiver can give a bit, and the receiver gets only the chosen input of the sender. Right? And it doesn't know anything about the other input. And the sender doesn't know anything about the choice. And how does it look like? Typically, oblivious transfer, it's a 2-message protocol, and this is how it looks like. There is a sender and the receiver. The receiver will initiate because the receiver has to get the output, and typically these are 2-move protocols. As you can see, the first one is initiated by the receiver. So the receiver does something with the input bit, and it has some randomness, R and the bit, and it does something and it computes XP. That is getting computed, sent to the sender, and the sender is computing something based on its input and the message that it has received from the receiver, and then it sends back. And with that, the receiver should be able to. This is actually the third message. So this is the first message that the receiver is computing with the bit and the randomness. This goes to the sender, and the sender computes OT2 message function on its pair of inputs x0 and x1, and the OT1 message that it had received from the receiver, that it sends to the receiver, and finally the receiver is computing the third function, which is OT3. Right? This is on OT2 message which it has received from the sender, and of course its state, which is the input and the randomness. So this is typical 2-move oblivious transfer protocol. So this is the fundamental result that I have been mentioning you. The problem of securely computing any general function f reduces to securely computing this elementary 2-party OT. Any function to oblivious transfer. I actually like this sort of transformation, this sort of simplification. You want to compute a really complicated function f. What this result is saying is that you only have to worry about computing a very simple function, which is oblivious transfer. And this task is very simple, right? It's very well understood. First party has 2 inputs, second party has a bit, second party gets only the chosen input of the sender. Right? So it's a much simpler task. So this is the importance of the reductions in cryptography, right? You have a much complicated task at hand, and you reduce that task to something much, much simpler. So in this case, it is that any function you have at hand, in order to compute that, all you have to know how to compute a much simpler function, which is an oblivious transfer function. So all these results I'm quoting there, I mean, thanks to them, this result is already known to the community. So as I said, we are interested in knowing the round complexity of MPC protocols which are relying on oblivious transfer, on the minimal assumption of oblivious transfer. So this is the problem. Okay, so I don't know if this will make, I think this will make sense. So how many of you have?
Still in the malicious setting or is this setting?
Both actually. Both. Yeah, both. okay, now I want to, so since I told you that any MPC for any function is reduced to oblivious transfer, so basically that bigger protocol is using this oblivious transfer as a building block. Now I'm telling you how is it going to use that building block as. So how many of you have done programming at some point of time in your life? Everybody. So you know what is black box users and non-black box users of underlying primitive. So I'm actually going to tell you that. So that makes sense in the protocol design as well. So there are two ways an underlying primitive can be used, right? Either in a black box way or in a non-black box way. I mean, it's the same way that we know from the programming perspective. So when a bigger protocol is using some underlying primitive in a black box way, that means that it just needs to know the input and output specification and it knows what it does, right? It doesn't need to know how the primitive, right, internal details of the primitive. So it can be agnostic of that, ignorant of that. Whereas in black box, non-black box access, the bigger protocol somehow uses the details of the underlying primitive. So that's called non-black box users. And typically black box access of primitives or the protocols which uses its underlying primitive in a black box way, they are valued more because they tend to lead more efficient protocols than the ones which uses the underlying primitives in a non-black box way. Because you utilize this underlying.
So maybe it's simple, but it's hard to say whether it's more efficient.
It is more efficient. So that's what for at least in MPC we try to design protocols which uses underlying primitives in a black box way, so that we don't care about how this underlying primitive is used. So for instance, you are using oblivious transfer, right? So so far you know some of these implementations, right? But later somebody would come up with a different implementation of oblivious transfer. So, but your MPC protocols still be using some oblivious transfer. So it is better if it is agnostic of the exact details. And typically these are
modular design instead.
Yeah, modular design. Not only that, so it actually leads to more efficient practical constructions, right? So okay, so now I want to refine the question. So the question that I was saying is that we want to analyze the round complexity of MPC protocols which uses oblivious transfer as the primitive, the only primitive. Now I want to say that I want to analyze the round complexity of MPC protocols which uses oblivious transfer as a black box way, not non-black box way. In fact, there are cases where you will see that if non-black box users is allowed, there is advantage in terms of round complexity. Less number of rounds are needed when non-black box access is allowed compared to black box. There are some instances. Very interesting in MPC. So we'll just review the round complexity over here, and then we'll move to one of the contributions, which is very simple. I guess I can cover in 10 minutes itself. So again, one round we can't do. So same impossibility that we discussed in the beginning, that still holds good here. In one round we can't do anything over here as well. So what about 2 rounds before that? Not before that. 2-round protocol is actually possible, and if you think about just 2 parties, here 2 parties are allowed because it's a dishonest majority case, right? 2 party, we can actually get 2-round protocol from black box access to oblivious transfer. And thanks to the very first protocol in secure computation, Yao's protocol, back in 1992, the first protocol that he proposed, without knowing of course, that is itself is a 2-round protocol which makes only black box access to oblivious transfer. What about when you go beyond 2 parties? Right? That is a hard case. 2 parties is an easy case. Yeah. Yeah. So that's what I'm saying. In this case, I'm interested both in semi-honest and malicious.
But like for malicious, 2PC also is 2 rounds enough?
No. But even for the basic case of semi-honest, 2 round is possible from just from Yao. But if you now go for multi-party, the first actually constant down multi-party protocol we have seen in the dishonest majority setting is BMR 90. Okay, and that gave a constant down protocol. It's constant, but it's it's not 2. It's much more than 2. Then very recently, 2017 and 2018, first time we saw a concrete 4-round protocol from black box access to 2-round oblivious transfer. It's a 4-round protocol, right? But what about 2-round protocol? Because in 2-party setting we already got a 2-round protocol. What about that? The next result actually shows something significant. It shows that 2-round MPC is impossible to achieve from black box access to oblivious transfer. 2-round MPC is impossible, right? So for 2 parties you could achieve. From Yao's protocol we know how to do it, but the moment you go for 3-party, 4-party or more than 2-party basically, it's impossible to achieve. It's a very
semi-honest or malicious?
Semi-honest. It's not possible to achieve from black box access to oblivious transfer. But what about non-black box access to oblivious transfer? It is possible, and that is actually the result I quoted in the second slide in the talk when I said that we are considering just semi-honest case, and then we consider this honest majority and a dishonest majority, right? So the dishonest majority, I said that 2-round is possible. So that's the result. But that uses oblivious transfer in a non-black box paper, unfortunately.
Is it semi-honest or malicious?
Both. They give both protocols, semi-honest as well as malicious, but the malicious protocol is in the CRS model if you know what CRS is. Okay. So this is a very interesting result. They show that in 2 rounds multi-party case you cannot get from black box access to oblivious transfer. So what is left then? If this is understood, 4-round is possible, 2-round is impossible. That means what? 3-round. That leaves the question, as an open question. Can we get a 3-round multi-party protocol from black box access to oblivious transfer? So this is something that we solve in this paper. Okay, and I'll just show you one technique for that. I still have 5 minutes for that, and should be able to do it. And this is in this paper we actually give protocol for both semi-honest and malicious, both the cases. And the idea that I will give is only for semi-honest, and malicious is significantly more complicated. Okay. So essentially what we figured out in that paper is that complicated task of doing MPC for any function f reduces to this simple function which we call as double selection functionality. Tell you what that is, but what we are saying is that, or what we figured out in that paper is that if you have any function to do at hand, right, you forget about that function. You focus on building a protocol for this simple function. Simple function, I'll tell you what the simple is, you will understand how simple it is. It's an extremely simple function, right? So that's what we say. You have a function complicated enough, forget about it. I know that you have to compute that function, but forget about it. You worry about computing this simple function. What is this is called a double selection functionality. So what is that? It's a 4-party functionality. First 3 are called Alice, Bob, and Carol. So first party has a bit. All of them are bits. Actually, all of them that you see are bits. So Alice has a bit. Yeah, somebody has a question.
What about that other red color shirt?
That guy doesn't have any input. That's you. You will get output. You don't have anything. No, I'm joking, sorry. So Alice has a bit which is alpha. So double selection, right? So alpha is the selection bit. Now Bob has a pair of inputs x0 and y0, and Carol has also a pair of bits y0 and y1. Now we have to we have to justify the name, right? So the functionality does as follows. Alice will, Alice's input bit will first select one of the bits of Bob. That's the first selection. X of alpha is the selected bit. Now X of alpha will select one of the bits of Carol, right? So which is going to be Y of X of alpha. And this is why it is called double selection. So Alice has a bit, and using that bit we select one of the inputs of Bob, and that is acting as another selection bit for the input pair of Carol. Right? So this is the outcome, Y of X of alpha, and this should be known to all the parties. This is called the double selection functionality. Okay, so again repeating what I said, if you have any function to compute, don't worry about it, solve this functionality, and if you solve this, then you can do any MPC and without adding more rounds. So whatever will be the round complexity of your double selection functionality, we will give you a way that you can compute your original function also with the same round complexity. You will not require more. So the compiler is round preserving from double selection to the MPC. So we will do exactly that. We will worry about solving the double selection and not the actual function. Okay, so now if you look at the degree of the output of this double selection function, what is that? I have written already it's 3. You will have to explain why it is degree 3. How can you write Y of X of alpha in terms of all the inputs alpha, x0, x0, x1, y1 and y0? How can you write it? Can anybody write? Huh? You can write Y of X of alpha, in terms of these inputs, and you will see that the degree will be 3. So this is a degree 3 function. So what we want to do is that using oblivious transfer in a black box way, we want to compute this double selection function. From 2-round oblivious transfer, we want to build a 3-round double selection function. Because the goal is to get a 3-round protocol, MPC protocol. And what I told you, promised you, that if you have a R-round double selection protocol, then you will get an R-round MPC protocol. Because of this compiler, I said that we don't need any extra round. If you know how to solve this very simple problem with some round R, then you can solve your original problem, which is an MPC problem, with the same round complexity. So can anybody give me now that protocol, double selection, using oblivious transfer? That is all is left out. Anybody has any thoughts there? Yeah.
So this YX alpha should be learned by all the parties.
All the parties.
Okay, and nobody can learn X alpha.
No. Nobody can learn anything actually. So the functionality is that all the parties will give their respective inputs. Y of X alpha will be known to all the parties.
But Carol will learn X alpha just because she knows what Y0 and Y1 are, right? So she'll know X alpha is 0 or 1.
Good, yes. But that's fine. And we have one last transformation. I think we are losing track, but I don't know. So this is a double selection functionality. From there I have a private version of it where the output is learned only by Alice, and if you can do that in 2 rounds, that will be it. So initially I asked that this has to be done in 3 rounds, and that will give you a 3-round MPC protocol. I'm simplifying this, changing this to that where the output is learned only by Alice. I'm saying that if you can do that in 2 rounds, doing this is easy actually in 3 rounds. Can you tell me how you can do it? So I'm saying that you have the left side, that protocol in 2 rounds. Can you give me a right side protocol in 3 rounds? Okay, so yes, your brain is working, fine. Yeah, so that's how if you have a 2-round protocol for that one, then a 3-round protocol is easy because Alice can simply sent to everybody. Yeah, good. So now the task is that you design a 2-round a double selection private functionality from a 2-round oblivious transfer. Why is it difficult? I'll tell you why is this difficult. Because DSLP, I mean that double selection functionality is actually a degree 3 computation, yeah. But oblivious transfer is actually a degree 2 computation. Oblivious transfer is what? It is outputting x of alpha, right? And since you have double selection, that is actually degree 3. So using a primitive which is doing degree 2 computation and to get a protocol which is actually doing degree 3 computation, the same number of rounds. This is also 2 rounds, that also you want as 2 rounds. So that is actually hard. Yeah, you have some question.
Just to follow up on the question, so in oblivious transfer, which if I'm asking for a p bit, the sender shouldn't know which bit I'm asking, right?
Yes.
But then here you are allowing that thing like x alpha is known to Carol or alpha is known to Bob. Is that
Alpha is not known to Bob.
Okay, alpha is not known,
No.
but x alpha is allowed.
Allowed because of the output. I mean, since from the output, Carol can find out, right? Yeah.
If you can do this private double selection in 2 rounds, I'm assuming this y x alpha is somehow encoding the output that you finally want to compute. So can you not have a version where the roles of these parties are reversed? Say another parallel instance where Bob is acting as Alice and Carol is acting as Bob and so on. And then that way Bob can also learn this via x alpha in 2 rounds. And that way every party can learn it in 2 rounds, right? So then you'll get a 2-round protocol.
Oh, you want to... No, so essentially actually this thing has... See, the requirement is that these 3 parties are giving input and a 4th party should know the output. It's not just that Alice knowing is enough. So in an n-party protocol, every 3 party will give inputs, right? And a 4th party should know this y of x of alpha.
Correct, but I'm saying you have this private double selection where Alice learns y x alpha, right? You can have a similar version.
Wow.
But if you change the roles, they don't know each other's inputs, right?
Yeah.
If you run it on the same input for everybody.
No, not for the same input. Maybe the input.
No, the same inputs, the same thing you have to know. So yeah, that's the thing. I think we will not go over finally how to solve this problem. It's a bad moment to stop. But I mean, if you have questions, you can come back to me. I'll show you the slides. Or you have already guessed the solution. Some of you. Did anybody guess how to build this? I mean, how to build? Any idea?
Overlap some messages.
I will overlap. I'll run several instances of
So can
oblivious
you
transfer.
write this 3 degree thing as a multiple 1 degree or 2 degree, 1 degree, split the function and then use this thing?
No, it's not that complicated.
Imagine you just make.
Yes, let's see what is the just after that. When you say just, that is something very trivial. Actually, it is easy, but still not that easy.
I do not have the exact equation, but I'm assuming one party can assume like for all possible values that.
So these are all bits. These are all bits.
Right. So for example, Carol can maybe generate like 4 messages. One assuming the first instance x0 was selected, and then in the second instance where x1 was selected. So now it boils down to like doing 2 parallel routing.
I think the idea you have got it. So essentially I'm doing exactly that. So I'm running 2 OTs between Bob and Carol. Bob is the receiver and Carol is the sender. Can anybody guess what will be the inputs for the first OT and what will be the inputs for second OT? It is along the lines what you said. Alpha is going to be, I mean the receiver's input is going to be for the first one x0, good, and the second one will be x1, and whatever the sender's input for both the OTs? Both? Who said both? You, good. So for both the instances there will be y0 and y1. Now can you tell me what will be the output of the first OT? I mean OT0. Good. And the second one will be y of x1. Now depending on Alice's bit alpha, we have to actually choose the output of one of those two OTs. So we basically need, so these are actually called inner OTs, these two, and then we'll have two outer OTs, right, which will be run between Alice and Bob and Alice and Carol to select one of the OT's output. Right? Then the output will be y of x of alpha. Right? So yes, so if Alice's alpha is 0, then we are going to choose the output of the first OT, I mean OT0, and if Alice's input alpha is 1, then we are going to choose the output of OT1. This is exactly what we actually do. So for these OTs, the inputs of Alice will be the receiver, its input will be alpha for both the cases, and what will be the Bob's input and Carol's input to the OTs. If you tell me that, then that's it. You want to figure out while having lunch, that's also fine. Can anybody guess what will be the inputs for that OT? There is something in the title. That's actually your clue. We had very fancy names: cascading OTs, selecting an OT via OTs. All these names are justified. What will be the input of the first OT? You just tell me, that's it. The second. Huh? x0, x1. No. Then Alice will learn x0 or x1. No, so if you feed here x0 and x1, Alice will learn x of alpha. That's not permitted. Or that's permitted. 0 and 1. What? Okay, 0 and 1.
Selecting the inner OTs, something like that.
So what does it mean by selecting the inner OTs?
I think it will be messages of OT, messages of this. That would be.
Will it be y of x0 and y of x1?
Let me actually spill out this thing. So basically when you are running this oblivious transfer, right, these two inner OTs, so these guys would have acted as receiver. So they had their input x0 and y0. You already said x0 is going as the input. So there is some randomness with which it has computed the first OT message, and that has been sent across. And similarly over here the input pair is x1 and some randomness r1, right? Along with this, Alice is running these OTs, and as I said, the input is alpha. Now this guy is acting as the sender for this, right? And these two sender messages are acting as the OT message for these outer OTs, right? So depending on alpha, either this one or this one will be obtained by Alice, right? And over there, that solves the puzzle. You were saying x0 and x1. Actually it is, the message is going to be the pair x0, r0, the randomness also. And over here the other message will be x1 and r1. Just giving alone this x0 is not going to solve the purpose. We also have to give the randomness that has been used by this party as a receiver. Right? Now that has been sent to Alice. Now depending on alpha, let's say that this is 0. So it will get this pair x0 and r0, and from here it will get this one, first one. So it essentially gets the OT messages corresponding to this OT, right? Now this guy Alice can actually act as the receiver, and it can get the output of this OT because it has got the receiver's message, it has got the corresponding sender's message for this OT, and then it can decode what it is, and that will give it y of x of alpha. So that's it, 4 OTs in parallel, and that's it. We are using it in a way that degree 2 computation allows us to compute degree 3 computation. If you did not get the last slide, I can explain you later, but go for lunch. So that's it. Yeah, thank you.
I guess questions will be answered during lunch.
Yes, yes, very much. I don't know. Yeah? Okay, come. For the photo purpose.
What you choose to do with it is here. What you choose to do with it is up to you.
Okay. No, I don't. Thank you.
Thanks.
Yeah.